So it is my very, very great pleasure to welcome and introduce our speaker, Professor Saiful Islam, who many of you, I hope, will have seen as the 2016 Royal Institution Christmas Lecturer. This is an enormous honour for any speaker. I wish I himself, I'm extremely jealous, but it is a fantastic honour to do Christmas lectures at the Royal Institution. They've been going for an extremely long time, having been founded by no less than Michael Faraday. Saiful himself has been at Bath since 2006 as Professor of Material Science. He has great expertise in many things, including batteries. But today he's going to allow us with a fantastic show, and I'd like you to all welcome him and enjoy the act.
First of all, I'd like to thank Chris for that kind introduction, but also thank you for coming. So welcome to the University of Bath. First of all, I was going around looking at the ages of this mixed crowd. So give me a cheer if you're 10 years and under. Give me a big cheer. Thank you. And give me a loud groan if you're 40 and above. So, as you can tell, a nice mixed crowd. So I'm a bit anxious about this talk. I can give conference talks quite easily, but I'm anxious about the level to pitch it. So, we've got a real wide age group. So I asked Chris, what should I talk about? And he said, about 45 minutes. So for about the next 44 minutes, hopefully I'll give you a sort of an overview, a bit of an overview of the Christmas lectures. There's a bit of a difference. Obviously, the 3D glasses I couldn't use unless everybody at home had 3D TVs. So I'm going to have a bit of a flavour. And as Chris said, it was a real big privilege to give the Christmas lectures. I have to say, I don't know if you know, but in the Guardian article, which when they interviewed me, I was honest. I said I actually declined them, first of all, because I was really scared about doing them. They're really high expectations. So anyway, let me move on to the theme, and it's really the talk menu. I'm going to give a couple of starters, a bit of an introduction on energy. Then the second, I suppose, starter will be about materials. One of the main courses is to do with batteries, and love them or loathe them. They've revolutionised portable electronics, like that mobile phone. And lastly, a bit of conclusions and concluding remarks. But as in true theatre style, hopefully you've turned yours off. So let me start off a bit about energy itself. I'm going to start off with one of my scientific heroes. And this is Michael Faraday on the back of the old £20 note. And he's one of my scientific heroes because he came from very humble beginnings, but he rose to become one of the greatest scientists in the world. And this shows elegantly, actually, Michael Faraday giving some of his Christmas lectures. And the subject of this lecture is really something that makes the universe tick and really is important for the world in this century, and that is energy. And a good place to start is really where Michael Faraday started on this topic. He was famous for giving lectures on the chemistry of the candle. And for the older members of the audience, there's 4 candles. Yes, obviously the younger ones, it goes over their head. You have to explain to them, show them the... he was famous for giving these Christmas lectures on the chemistry of the candle. And he wanted to show the principles of energy and chemistry to the candle. And this is one of the first demos I did on the Christmas lectures. It's a really tricky one, but it does show quite elegantly what I'm trying to get across. So the idea is, can we relight that candle when I turn it up, when I actually get the wick out? can we relight it without touching the wick? It is a bit tricky, and I might do it a couple of times, but I've got a slow motion of it. But let me see if I can do it here. It is a tricky one. So let me do that again. It always works in the rehearsal, but not here. So let's see that again. So you can see the vapour going up. It's a bit breezy. I'll do it once more, then I'll show you the slow motion. Thankfully, we've got something that we prepared earlier. So let me try that again. No, it didn't quite work there. So let me just show you what we have. Okay, so what you see here is a slow motion of what should have happened there. And you can see the candle at the bottom that I'm pointing to. But at the top is not the flame from the wick, it's actually the flame from the lighter. And what you see is that at some point when I carry on playing that, the actual wick is actually relit without me touching the actual candle. So let's see if that happens there. So this is a clip from... So you can see the wax vapour, just about see the wax vapour there, and it's going to right there. So that's what's happening. So that was a slow motion. Hopefully I might have a go at that later on again. What that shows quite elegantly is that that candle is converting energy from one form to another. And that's one of the important principles behind the conservation of energy. So the conservation of energy says that energy can neither be destroyed nor created. It's just transformed from one form to another. So that candle, what's happening there, the candle, you're transforming basically the wax energy, the chemical energy from the wax, to light and heat as well. So if you're close to it, you can actually feel the heat. So that's the conservation of energy. And that's a very important principle. You can't create energy. Another important principle is the word power. And scientists are very keen to distinguish between the words energy and power. And we're going to show this, hopefully. We haven't trialled this again, so hopefully this one will be working okay. Oh, I have to introduce Emma and Maya. They're both PhD students here at the University of Bath. They're within the doctoral centre called the Sustainable Chemical Technology. So they actually work in this clean energy area. So let's give this a go. So shall I do it on this side? So let me light it first. See, this long stick always implies that it's going to be a really dangerous experiment. But we don't know. We haven't tried this out before. So this candle, this sort of candle, is made of sort of a fire paper, and hopefully it's a bit more flammable than the... so if the cameraman's ready there, let's give it a go. Oh, yes. I think it deserves applause, yes. You may think that there was actually more energy in that particular candle than the first single candle. But actually, the energy content is very similar. The difference is power. The actual amount of power in that last one is released. And what power is actually how fast energy is transferred. In this case, from that candle to light to heat, and actually a bit of sound as well. You could hear a bit of sound from that. So that was quite an elegant experiment showing the difference between energy and power. And, oh yes? So when we think of energy, the word that comes up a lot is the word electricity. When we think of powering our homes, we think of electricity. So electricity isn't always easy to see. Basically, it's a flow of electrons. Can we see electricity in the raw? So I was very fortunate because it was the 80th anniversary of the Royal Institution Christmas Lectures. It was 80th birthday of when it was first broadcast by BBC TV. In fact, it was when Science TV was born back in 1936. I could invite Christmas lecturers past, and because I'm really keen on championing diversity, I tried to invite as many of the past women lecturers as I could. I don't know if you know that only 6 women have given the Royal Institution Christmas Lectures. Hopefully it'll be better over the next 80 years. So I invited all 6, only 3 were available, but I managed to get Monica Grady, who you'll see here, lecture 1. I managed to get Alison Woolard in lecture 2, when we talked about food, and Danielle George in lecture 3, when we talked about energy storage. So I managed to persuade Monica Grady to do this, and we managed to find the largest Tesla coil. I'll show you the clip, and I'll tell you more about it afterwards. So she's sitting in a Faraday cage right next to the biggest Tesla coil in the UK. So they are electrical sparks. It's a bit jagged, this video. I think it's because of those sparks. Right, so rather her than me when she did that. So what's happening there? Well, what's happening is you've got this Tesla coil which builds up a lot of electrical charge and releases it in a big burst. And the air around us, is actually a very poor electrical conductor. So that spark comes out in bursts. And obviously we see that in nature through lightning storms. But electrons prefer, if it can, to go along something that's more conducting. In this case, a metal cage, which in this case is the Faraday cage. So in principle and in practice, if you're inside that Faraday cage, you're safe. So it's obviously named after Dr. Cage. No, Faraday, obviously, yeah. So how many of you have actually sat, just like that child there, Monica, within a Faraday cage? Yes, the ones who put their hands up know what I'm talking about. Actually, all of you have sat in a Faraday cage. The cars that we drive are essentially Faraday cages, because if there's a lightning storm, what that car is doing is actually, it'll protect you from being electrocuted by that lightning. So when we think of electricity in the home, how is it mostly generated? Well, most of it, although the amount has decreased in terms of electricity, most of it generated using fossil fuels. So coal, gas, and oil. And it's obviously a very big, hot topic, both literally and metaphorically, in the sense that fossil fuels are actually releasing a lot of carbon dioxide, which is a greenhouse gas, which is there's strong evidence that's leading to man-made global warming and potential climate change. But where do fossil fuels get their energy from? Well, basically, if you think about where coal, gas, and oil come from, they are essentially plants. From millions of years ago, they are from the sun. Those plants decayed, and you get, so essentially, a lot of the electricity we get is solar powered, in this case, in the form of fossil fuels. So the next question, because that's a massive nuclear reactor, we've got the hydrogen. So what's bubbling away to produce and to actually transfer that energy? It's basically hydrogen. And we can't have a lecture without a hydrogen balloon, surely. I could show you the hydrogen balloon. Shall we actually pop it or not? So it's hands over ears, please. It's just in case, so hands over your ears. Yes! No applause. It's a good one, isn't it? Yeah. So obviously we've actually ignited that hydrogen. how does the sun get its energy? Well, obviously, within that massive nuclear reactor, there's something going on. It's actually, as I said, converting hydrogen from one form to another. And this leads on to probably the most famous equation that we know. So all shout it out, E equals... Thank you. So it was formulated over 100 years ago by one of the greatest scientists that ever lived, Albert Einstein. And there he is writing it there. So E is for energy, M is for mass, and C is a huge number, which is the speed of light. But what it's telling us is that essentially mass and energy are interchangeable. You can actually create a lot of energy from a small amount of mass. And that's used, unfortunately, in probably the most destructive weapons known to man, that is the hydrogen bomb and the atomic bomb. But it can be used more, hopefully, more reasonably. So we tried to look at some detailed calculations of how we could illustrate the effect of E equals mc squared. And we came up with basically my pants, which is poor Emma is holding. So we got my pants, which are pretty powerful. So let's see so we thought there's enough atoms in there to power Birmingham, lucky Birmingham. So we're going to try and see if we can generate and transfer enough energy to generate Birmingham. So we don't know, it's actually, we've speeded up this reaction by having some acetone in there. So, whoa! Yes, right, that's pretty good. So would that power Birmingham? We have a scientific term for that. It's liar, liar, pants on fire. And they are, so should we let that go? Let's try it out. So, yeah, that was quite good. I like that. So, but what would, though, how could you power Birmingham with those pants? Well, you'd actually need to do proper nuclear fission. Basically, it's a series of very powerful nuclear reactions that breaks up the atoms in those pants, not the bonds. What's happening there is that the bonds are breaking up, and that's what's actually burning up. But here, nuclear fission, you're breaking up the atoms, and that's how a nuclear power station works. So let me take a sidestep a bit towards an area that I work on. Probably one of the most important aspects of energy right now is, can we store energy more efficiently? Because if we have renewables like wind and solar, we need to store the energy when the sun isn't shining and the wind isn't blowing. So we need to store that energy. And currently the best way to store energy, or one of the best ways, is the humble battery. And it's really revolutionised portable electronics. For those my age and for those who've grown 40 and above, we know a time when our children weren't hooked onto portable electronics. So they've revolutionised. So there's my old iPod, laptops, mobile phones, tablets, all rely on lithium-ion batteries. And that's because they've got something called a high energy density. They can store a lot of energy in a small amount of mass and a small amount of volume. Okay, so you can see my taste in 80s music there. Right, so size obviously matters. So again, unless you've got large pockets, they're the kind of phones that people are walking around with on Wall Street and others. So thankfully we've moved on from that. So what's the next challenge? Well, the next challenge is they've been successful in portable electronics. Can they be developed for electric cars? Can we electrify transport? They're not completely zero emission, and I stress that they're not zero emission, but they would reduce the amount of CO2, the CO2 emissions. So there's a little bit from the Toyota Prius, which is sold over 6 million now. There's the sexier end, the Tesla sports car, and Elon Musk of Tesla is bringing out some new model Tesla cars. And all the car manufacturers, the Nissan Leaf up in Middlesbrough are producing electric cars, BMW i3, the Renault Zoe. So every car manufacturer are coming out with electric vehicles. And the reason is that road transport accounts for about 30% of all CO2 emissions. And the problem with that number is predicted to rise because of fast developments in India, China, and Brazil. So we really need to move away from using petrol and diesel within cars. But there's the problem with current batteries. They're not good enough. So my research is looking at new materials. So this is where I talk about crystal gate. So we live in a crystalline world, and one of the best examples of crystals are in your kitchen right now. Salt. Salt is made up of those tiny crystals, and on the atomic scale, they look like that title slide. So on with your 3D specs. So that's the stuff that you sprinkle on your chips, on your rice, in my case before a tequila shot. So that is sodium chloride. The large spheres are chloride atoms, and the small ones are sodium. So as in politics, red is on the left, and for the best effect, if you stare and move your head side to side, even if that doesn't work, it makes me laugh from this angle. So hopefully you can see it's quite a 3D image. But there's an important property of solids, and that is the fact that some solids show ion conduction. Most of the ions stay where they are, but some of the ions. So if you stare and move your head side to side, let's see if this works. Yes. That's a good one. I'm going to try it out from the back. I need some glasses. I've got some glasses here. Yes, so I'm going to do that again because I like that so much. Yes. I'm going to block the camera. All right, red is on the left. See if it works. Right, let's have that again. So I want to ooh this time. Give me an ooh. Ooh, yeah, ooh, yes. Ooh. Thank you. That's great. So that ion conduction will become important when I talk about the next thing. So my research is computer modelling. So when I go to parties, that's when I'm invited, that is. Somehow when you mention you're a chemist, suddenly the invitations dry up. So when I go to parties and they ask me, what do you do, Saiful? I say, I model. But obviously not down the catwalk. I am a chemist that doesn't wear a lab coat, even for explosive demonstrations. And what we do is we use very powerful supercomputers. So for the youngsters out there, if you're into chemistry, into physics, but don't want to actually touch anything, a bit like Sheldon in Big Bang Theory, then you could use these supercomputers to do computer modelling. So what is computer modelling? Well, basically it's model building. And this is one of the iconic photos. So again, for the youngsters, this is one of the most famous photos in science. This is Watson and Crick in Cambridge in 1953, and they built up using retort stands and clamps the structure of the molecule of life, DNA. They worked out that in fact it was a double helix. And what you can do now is supercomputers, and they got the Nobel Prize for that discovery in 1962. You can do that on supercomputers within seconds. You can build up that model. So that is model building. And what is important is that if you understand the structure of something, you begin to understand more about its properties. And also I want to stress that this is a good illustration that basic science can lead to really profound understanding of the world we live in and about us. Because they just did some basic structural work and they found out the structure of DNA. So how does modelling work? Well, modelling works by looking at the bonding of structures in all dimensions, and in this case, it is ionic bonding. So I've called this, the name is bond, ionic bond, and so you've got modelling forces there. Right, so what's inside? So if some of you ask me, Saiful, what's inside a lithium-ion battery? I'd say that's a very good question. And I'm going to try and explain to you. This is probably the most complex slide I'm going to show you, but I'll try. So basically a battery, view it as a sandwich. So you've got two bread slices, and then the meat, or cheese if you're vegetarian, between them. So in this case, the bread slice is a positive electrode made of cobalt oxide. The other bread slice is graphite, just carbon, and in between is a lithium salt, allows lithium conduction. So how does your battery in your phone work? Well, think about this. You've got that red sign. If you want to charge it, you plug it into the mains. And all you're doing is moving lithium ions from one side to the other, and the electrons are coming from the mains. When you want to use your phone, you just discharge it, and the lithiums are going the other way, and there. So basically, you've got just the shuttling of lithium from one side to the other. And lithium is the smallest metal atom in the periodic table. Okay, so that's basically inside. So when you see those red and green symbols tonight, just imagine chemistry in action. Lithium ions are moving. So before I show you some more 3D images, I've just got to explain a bit about atomic structures. So this is a metal ion in blue and purple, and around it are 6 oxygen atoms here and 4 oxygen atoms here. And they can be represented in a different way. They can be represented by this octahedron, just showing the points, or they can be represented by a tetrahedron, a bit like a pyramid. The reason I wanted to show you that is that you'll understand the next 3D images, the final 3D images, a lot better. So 3D specs again, red on the left, and jiggle your heads about. So this is actually the compound in your mobile phone right now. It's a cobalt oxide material. So you can see these sheets of cobalt oxide, these sheets of cobalt oxide, and then these sheets of lithium. So the lithiums will be coming in and out. And as in life, the important stuff is happening between the sheets. I should go back. Cobalt is a problem. I mentioned that we want to use these in electric cars. There's a problem with cobalt. It's both expensive and toxic. So there's a big drive to try and replace cobalt with other metal ions. So one of the cleanest or environmentally benign elements is iron. Iron is all around us. In fact, rust is obviously, so you could make materials out of rust. So even if you're not a chemist or a structural chemist, I hope you can see straight away this structure is very different from the one I've just shown you. This is lithium iron phosphate, so for the chemists among you, I've given you the formula, but hope you can see the octahedra and then the tetrahedra connecting up. And this is known as the X factor of materials because it's non-toxic, it's cheaper, and it's safer than the cobalt oxide. So it has potential to be used in electric cars. So how does it conduct lithium? How do the lithium ions move? In this case, they move through those channels, so it's a bit like a tube train in London. They go through one-dimensional channels, and they come out that way. Okay, so that's the same motion of lithium as I showed you in the other structure. So keep your 3D specs on. This is a 3D image. I'm part of a research group. There's kind of images of chemists and scientists in the films as us working alone with bubbling liquids is far from the truth. Usually you work in teams. So my team worked with a group at the University of Strathclyde in Glasgow. And you may not believe it, but that is our test vehicle. That beautiful AC Cobra, we put in lithium batteries in there, fuel cells, supercapacitors, and we test it driving around Glasgow. And as you can see from what they're wearing, it was a relatively warm day in Glasgow that day. Yeah. And my last 3D image, this has nothing to do with batteries yet, but I thought I had to show you. So move your head around. I'm not going to stand in front of it. It's amazing how those antennae follow you around. It's a bit creepy. So that's the wake-up call, just in case you've nodded off already. So that's it. That's the millipede, and that's right. Yeah, I'm glad it's looking up. Great. So a bit of interlude. So this isn't 3D. So one of my group members, I'm in for diversity, so I've gone for species diversity. So this is Carla, the cat chemist. She's called the cat chemist because she works on catalysts, and she wanted to get into this talk by hook and crook, so she persuaded me she gave me 2 PowerPoint slides, and they are related to lithium battery research, because on the graphite side, they could replace graphite with silicon. So she said, is silicon the same in Spanish? See? Yeah? Yeah. It's Carla, don't blame me. And then the next one, she said, rumour has it that oxygen is dating magnesium. OMG. Yeah. Right, so I begin to conclude now. I hope I've given you just a flavour of some of the green energy research going about there. But I think we're at the dawn of a new era in clean energy, despite the new US president. But I'm optimistic, I'm a naturally optimistic person, and that greener energy mix could include solar, renewables, next generation biofuels, wave, and we can do our bit by energy conservation, by reducing the amount of energy we consume. But at this point, I could have used the profound quote from a Nobel laureate or a US president, perhaps, but I went with a different philosopher, something hopefully you'll appreciate, and that's Kermit. It ain't easy being green, and he's right, it's not easy being green, but as I said, I'm optimistic. So what's the future? One thing is certain about the future, it's uncertain. But I think you're going to see more solar power. You're already seeing it now in terms of households, industry, and I think you're going to see more electric vehicles out there as well. They could be hybrid, they could be purely electric. And really, as I said, I'm optimistic as a scientist, and I think it's a great time to be a scientist at this point. There's some great challenges in energy, in health, in medicine, and in nanotechnology. And really, in terms of the future, the future is really in your hands, the youngsters' hands, and I think, hopefully, there'll be some major discoveries from some of you out there. So, I thought I'd do a bit of history. Some people kept asking me, what's your background? So I thought I'd show you a bit, very quickly, a bit about my education. I went to a comprehensive school in Crouch End, London. That's you can see my mum used to cut my hair because it wasn't quite. She put I think just a bowl around my head and just went around it just to stay funny. So I went to. Unfortunately, that school doesn't exist anymore, and my junior school doesn't exist anymore in Crouch End, which is a bit sad. I then went to University College London, and really, my tip to the youngsters is follow your passion. Whatever you're passionate about, whether it's to do with any aspect of science or creative arts, whatever, but follow your passion. But a lot of it is hard work. If you talk to the athletes during the Olympics, it didn't come to them naturally, they had to work hard at it. So I was fortunate that I did, and I was very fortunate working hard. I managed to get into University College London, and then after my PhD, worked at Kodak labs in New York. So again, for the youngsters in the audience, that is called photographic film. Yeah, we used to produce that. Yeah, we used to stick it in the camera and develop it. I know it's a bit mad, but... and then my first academic job was at the University of Surrey in Guildford, and then I joined University of Bath about 11 years ago. I'm very happy 11 years. And then, as I said, it was a real surprise and privilege to be asked to do the 80th anniversary Christmas lectures. And it was probably the most stressful thing I've ever done. It would start around September, the filming was in December, and during that process I was thinking, what have I done? What have I let myself in for? It was just the aspect of the filming, the live audience, learning the scripts, thinking of demos. We had to have demos every 2 or 3 minutes, and so it was. I didn't have grey hair before I started those. So if you want some more information, you can Google Saiful Bath. I promise you won't get a dodgy image. And I was forced to join Twitter. If you're welcome to keep these 3D specs, but if you want to return them, we recycle them. And you're welcome to take some selfies, and if you can tweet them, you can tweet them with the hashtag 3DSpecsChem. You can see some past ones, and even some other well-known people have got into the act as well. And lastly, I'll end with the F word. The F word in this case is feedback. As university lecturers, we're asked to get some feedback from our undergraduate students. So I got this lovely bit of feedback, I thought, from an undergraduate student. And he or she said, if I only had 1 hour to live, I'd attend one of your lectures. Oh, yeah. Because it would feel like an eternity. Oh, that was great. Yeah, thank you. So, right. So this is tradition. So we're going to end, obviously, with just like the Big Bang Theory. We're going to end with some bangs. And we've got Emma, and this time I have to wear a lab coat, apparently. I don't know why. Just to prove that I'm a chemist. So, I don't know if we can, for this final one, can we dim the lights? Because there's some coloured flames here. Actually, give me, even with your hands over your ears, give me a bit of a countdown. 3, 2, 1. Yes. All right. So these next 3 are a bit different. So watch out for the colours. We've put some metal salts in these ones. So hopefully you'll see a bit of a colour difference. So 3, yes, go for it. 3, 2, 1. Oh, yes. Do you see that? It was a bit orange, wasn't it? You see that? Yeah. All right, this has got a different salt in there. This one has got barium. So what do you do with a dead chemist? Barium, yes. Okay, 3, 2, 1. Yes, you see that? That's more green. And this one is magnesium. This is the OMG. Magnesium, yeah. So, 3, 2, 1. Oh, that's in victory. Yes. Thank you for coming, and I'm happy to take questions. Thank you.